All right, so welcome to DataLab6. For Comm843, we're going to look at a multi-level model to capture bivariate associations. So the association between two variables. I'm going to be focusing on curiosity and happiness as I have throughout the data lab, but you can feel free to think about two variables that you've been working with throughout the course or other ones that are in the data set that you want to tackle. So we're extending things from the intra-individual correlation and intra-individual regression to capture something that is more likely going to make its way into a paper. The multi-level model is an extension of linear regression, the linear regression that we know and love. And this is a particularly good example by Michael Freeman at the University of Washington. It's just a couple of pages, interactive PDF type thing that walks through why you might want to go to the multi-level case. But the big takeaway is that when you have nested data, and in the example, he's looking at different faculty who are nested in different departments. In our example, we're looking at 21 days that are nested across 78 different individuals. When you have this type of nested data, you can't really make an assumption that your different data points are independent from one another, which is one of the assumptions we typically make in regression. Because I have multiple data points from the same individual, it's likely that there's associations between the data from that same individual. So my day one is going to be more similar to my day two than it would be to a data point from another person's data set. And so we need to kind of take this nested nature of the data into account, and the multi-level model allows us to do that. So there are three things that the multi-level model allows us to do that are most important for the purposes of this class. It helps us to distinguish between person and within person levels of analysis. So we can ask questions about do people who have high happiness on average also exhibit high curiosity? So that's the between person level. But we can also ask questions at the within person level. So on days when my happiness is higher than it usually is my curiosity also higher than it usually is? The multi-level model allows us to account for time, and we'll go through two ways that the model can account for time that are important for making sure there's no confounders when we're looking at bivariate associations. And it also allows us to examine between person differences and within person processes. So we will get a kind of an estimate of the prototypical within person association between happiness and curiosity, but we can also have the flexibility of modeling between person differences. We saw that when we drew scatter plots for the association between curiosity and happiness for different individuals, that there could plausibly be lots of individual differences happening, and we want to be able to accommodate those. All right, so this is a multi-level model equation, and we're going to walk through it. I've written it in this multi-level form, so it's two levels. You will also see it written as just kind of one equation where the levels aren't so explicit, but it's the same underlying math. But I like doing it in this two-level format because it becomes a little easier to focus on things that are time varying. So at level one, you have things that are mostly changing from day to day. And then at level two, you are modeling between person differences. So you can kind of think of the level one as time varying stuff and level two as time invariant stuff. Okay, so what this model does is we're going to model curiosity for person I on day T. So I is throughout here is telling us about something to do with people, and T is day of study. And we're going to model this with an intercept, which is the expected mean curiosity when other variables are at 0. So for example, what is the average level of curiosity for a person with average level of happiness? You can imagine that there are 78 of these, so that's why it has the I after this intercept. We're then also going to model a slope for the effect of day's happiness on day's curiosity. So this will tell us about within-person differences, how within-person differences in day's happiness are associated with changes in curiosity. So a couple of things to notice here is that you have day's happiness for person I at time t, so it's time varying, and this will correspond to the within person variable that we created when we split our predictors into within person, between person components. Okay. We're also going to include day of study. So this is something that changes. It goes from 1 to 21, or as we'll see when we actually do it, we're going to center it in such a way that it makes the intercept a little bit more meaningful, but that's not a huge deal. We'll cross it when we get to R. But so this is day of study for person I at time t, and we include this for reasons that have to do with confounding. So the reason we account for day of study is that when you look at these two variables, so imagine this is curiosity for one person and happiness for another person, across 10 days, we could extend it to 21, but the takeaway is the same thing. As curiosity, as the study goes by, there's an effect of time such that curiosity increases and happiness increases. If we were to then kind of run some sort of correlation analysis or regression analysis to look at the bivariate association between curiosity and happiness, we would see a positive correlation because look, as curiosity is going up, so too is happiness. But this is probably due to time, and time is a confounder. It's probably not due to anything about the association between these two things. It's not like, for example, curiosity is impacting happiness and happiness is impacting curiosity. It's driven entirely by the effect of time. And so we don't want to run an analysis and come away with the conclusion that, oh yeah, it's all about the association between happiness and curiosity, when really it was just about the effect of time on both. So one way to kind of deal with this is to account for, to include time as a predictor. And so in our case, that's what we're doing with day of study. This should have a beta 2i in front of it, by the way. Okay, so then we could add other predictors here if we wanted to. We're going to go with this simple model for now. And then this is, these are day-specific residuals for person I at time t. And these are often allowed to autocorrelate AR1. We'll talk about what this means in a second. You can think of these as deviations from the actual curiosity scores after taking account of our predictors for each person. So let's dig into that a little bit more. So our day-specific residuals, they capture unexplained daily variability in curiosity. So these are residuals or the unmodeled emitted effects that could affect curiosity, but that we haven't included in the model. They have a variance, so sigma squared is a variance of these residuals. And we typically assume that these residuals are normally distributed with a mean of 0 and a variance of sigma squared. We don't have to make that assumption, and in future data labs, we might see what happens when we relax that assumption, but that's not super common to do that. So we'll just focus on this case for now. And as I said earlier, we typically build in serial autocorrelation. So we have the residuals being modeled by a parameter that picks up the autocorrelation between adjacent error terms. So if I know something about my day 1 residual, I know something about my day 2 residual, is what that's saying. Plus within person random effect purged of autocorrelation. So let's dig into that a little bit more, because that's a lot of complicated stuff that I just threw out there. This is really nicely explained by JP Lorenzo of Boulder and Lorenzo Intensive Longitudinal Book fame, who I talk about all the time in his YouTube video on multi-level modeling in the context of intensive repeated measures. And again, he's kind of going through this idea of why we might need to account for the autocorrelation in level 1 residuals. So you have this line, and you can think of residuals as the distance from the data points to the lines. In your kind of ideal case where there is no autocorrelation in level 1 residuals, so this row value is at 0, your kind of residuals look kind of like randomly scattered. There doesn't seem to be any particular association between adjacent points. But when you have high autocorrelation, you see a pattern in your residuals. It's not uncommon to see something like this in intensive repeated measures data. The example that JP Lorenzo gives is, for example, maybe this is your mood on day of the week. And so on Sunday, you had high positive mood, but then you go into Monday, Tuesday, Wednesday, Thursday, and you see this kind of slump in mood. And then as you start to get the weekend, your mood goes up again. And If we hadn't included day of the week in our model, this pattern would be in our residuals. So by kind of modeling this autocorrelation in the residuals, and so that basically is taking into account the fact that adjacent residuals, if you know something about one residual, you know something about the adjacent residual. You basically introduce a placeholder for time-varying predictors that we haven't yet included in the model. So for this example, it was day of the week. What happens if you don't account for autocorrelated residuals? You essentially get biased standard errors, and we don't want that. Okay, so that's why we did that. And so with those previous two examples, that's two ways for accounting for time in different ways to avoid confounding. All right, so that was the level 1, and that was mostly about the time varying stuff. So you notice that there's lots of T's in this level 1, indicating time or day of study. And then when we go to level 2, these are about person-to-person differences, between person differences. So these coefficients at level 1, there should be a beta 2 here again, could vary from person to person. And so they themselves are modeled at level 2. And so you can notice there's an equation for each parameter in level 1. There's an intercept, the slope for day's happiness, and the slope for day of study. So this intercept is modeled as having an intercept itself, which is the average value of curiosity in the sample of 78 people that we have. This effect is our usual happiness variable. So this is the between person version of happiness that we created when we split predictors in the previous study. And this tells us the between person effect of happiness on average curiosity. So each person has one of these values. That's why it has an I. It's not associated with a T because the value of usual happiness doesn't change from time point to time point. So this estimate would tell you if you're a person, if people high in usual happiness are also high in usual curiosity. This is a person-specific residual. So this was day-specific residuals. This is now a person-specific residual in the intercept. And that's not explained by what's in the model. So people can have different average levels of curiosity is basically what this is allowing. And we want that. We saw from the plots we made in one of our data labs that there were lots of between person differences in people's average happiness, also people's average curiosity. For beta 1, now we're looking at the effect of day's happiness on day's curiosity. We can model this slope as having an average slope for the day's happiness and curiosity association. So what does it look like for the prototypical person in our sample of 78 people? And we can also model residual between person variability in this slope. So again, it allows the slopes to vary across people, and that could be important, especially given the scatter plots we saw, where there seem to be individual differences in the strength of association between day's curiosity and day's happiness. Here, we're accounting for the effect of day of study on curiosity. Notice that there's no U, so we're not estimating a random effect, or in other words, but we're not estimating between person variability in how time in the study affects curiosity. We could if we wanted to, but I'm just showing you that you have flexibility with whether you're going to model between person differences or not. Because this is not kind of, I'm including this as a compounder, it's not something I care substantively about. I'm just including the gamma parameter. Okay, so let's talk a little bit about these between person random effects. So these U's. The U's vary from person to person, the values of U's. This is where we introduce between person differences in our intercept and our slope for the effect of day's happiness on day's curiosity. So they can be different. And kind of as part of this, the multi-level model estimates a variance covariance matrix, which is what you're seeing here, which tells us about things like between person variance of the intercept random effect, tau 0, 0. So this is between variance of the random effect, variance of the slope, and then this is covariance between the random intercept and the random slope. This is also the covariance between the random intercept and the random slope. It's a diagonal matrix, so these are equivalent. And these these random effects are assumed to be normally distributed. This will make more sense when we look at the OR output. I just wanted to let you know that this exists so that when we look at the OR output, you know why we are seeing this kind of part of the model. Okay. Again, assumptions. So we're going to, this is kind of the kind of brief overview of the multi-level model I wanted to give. And when you're kind of running these models and looking at the data that's going in, many of the assumptions that come with linear regression also apply to the multi-level model. Here are just some of them. One of the kind of main ones that I wanted to highlight, just because it's different to what to one we would find in linear regression, is this assumption of stationarity. So the mean, variance, covariance, and autocorrelation of your variables are assumed not to vary over time. This can be problematic if there are, for example, systematic time trends in the mean, and those are relatively easy to see, and people will often, they will detrend their data if they need to, if they see like significant growth in their variables over time. But when you start applying these data, we can start talking about that in our office hours. Okay, and another thing I wanted to note is that confounders are still an issue just because we're doing slightly more complex modeling, and this goes for pretty much every modeling we do. It doesn't solve basic issues like causality. We can still only talk about associations. We can't talk about causal effects. We can try to, and we can use theories, and we can try to rule out confounders, but just kind of don't forget the basics is what I'm saying, design basics. Because they are in every kind of modeling stuff that you do. And this is part of the reason that we control for time, because we know it's a confounder. Okay, so I think that's it for the slides, and now we're going to head over to OR. All right, so now that we've gone through the multi-level model in our slides, we are going to turn to OR and run a multi-level model on our data. So we're telling OR where our data are, we're loading in some packages, I'm reading in the data, and I'm making my curiosity variable. I'm splitting my predictors, just like I did in DataLab6. So this is just copy and pasted code. And then a new thing I'm doing is I'm centering day of study so that 0 for the day variable is the middle of the study. This just makes the intercept, it means that you interpret the intercept slightly differently. It's like the average curiosity for a day in the middle of the study. And I don't know why, but I like that. And we can just double check that our data is actually doing that. We have 21 days, so when I subtract 11 from the 1 to 21 value, my first day is now -10, my middle of study is 0, and my last day is 10. All right, so we're going to use an LME to run a model. You may have to install this. And then we're going to call our model model1. You can call it something else if you like. This is part of the call, so you don't have to worry about that. And what we're doing here is we're specifying our outcome variable. So it's my curiosity variable. Again, you don't have to worry about splitting your outcome variable into within and between components. Because you've split your predictors, the model will do that for you. So you just have to do your raw outcome variable that you care about. And now this is saying, okay, that was my outcome variable, and everything on this side are my predictor variables. One is just specifying that you want an intercept. I think if you exclude this one, it will estimate an intercept anyway. The reason that this works is that my favorite statistical trick is that when you regress onto a constant, you get the mean. Thank you, Mike Rovine at Penn State, for teaching me that. And so that's just our intercept part of the model. Our happy within is our within person happiness variable. So this is at the level 1 part of our equation that we saw, and this will tell us if happiness is higher than usual, is my curiosity also higher than usual. We're also going to include usual happiness. And so notice now that even though we wrote our equation in this level 1, level 2 way of things, OR doesn't see that. You don't specify level 1, level 2 stuff in OR in any explicit way. It will know just because this is the same value for all the 21 days of an individual, right? It's not changing, it's time invariant. And then this is us controlling for time. So that's the main part of it. We're telling OR what data we want it to use. So we want it to use our daily diary data. And then here is where we specify random intercepts and random slopes. For this first model, I'm just specifying a random intercept. So I'm allowing people to have different average values of curiosity. And then I'm telling OR how to deal with missing data. And this is where I'm specifying the AR1, the autocorrelated residuals that we also talked about in the presentation. So just to give you some more detail about this, we're saying that the intercept is nested in ID. So that like line thing there is telling OR that we want it to be nested in ID. So we can run this model, and then we can get the summary of this model. And I pasted the output here earlier and commented it out. So let's go to the kind of main things that you would care about. So these are the fixed effects. You have a value for the intercept. That's the trash folks outside picking up my trash. So working from home is a joy if you can hear them sounding their horns. So here's the intercept, which is the average curiosity when all the other predictors are 0. Significantly different from 0 is what this p-value is telling you. And then this is your coefficient telling you about the within-person association between happiness and curiosity. So it's positive and it's significant. So it's saying that as my happiness increases, or as a person's happiness increases, their curiosity also increases. And so you can think of this as like, this is pooling everyone's data and giving you an estimate for like the prototypical person in your sample. This happiness between is telling us about between person information. So people who have higher happiness than the average person, or if you're a person who has high average happiness, you also have high average curiosity. So it's a positive number. And then this is saying that there is an effect of time on curiosity, such that curiosity increases a little bit throughout the study. Let me see. We can see our number of observations. So these are the number of days that we have available. You'll notice that this is fewer number of days than our daily diary data set has. And this is because people don't have curiosity values for each of the days that are available. And then we have our number of people. This is telling you about the variance of the intercept and the variance of the residuals, the day level residuals, and also the autocorrelation in the residuals parameter. Let me see if there's anything else I really want to talk about. Okay, the other thing I like is using this intervals function. Sometimes your model will run and it will even give you a summary, but when you run intervals, you'll get like an error message. And so I like to do it just as a check that my model is appropriate for my data and that there aren't any kind of hidden errors out there that I don't know about if I don't run the intervals. But I also run it because it gives me confidence intervals for all of the parameters, which can be useful. So you have your lower, upper estimate, and then the estimate. Sometimes I like to push these to where they should be so that I don't get confused. So let me see. You have your intercept random effect with your confidence intervals, the autocorrelation estimate, and then the day level residual. Okay, so that's neat. But in the previous model, we just had a random intercept. So in the random effects, we just had 1. But it's plausible that the association between happiness and curiosity changes, is different depending on who you are. We certainly saw some evidence for that in the raw data. So let's account for that. So the way you do that, everything else is the same. I gave the model a new name so that I know it's a new model. But I'm adding +1 or plus happy within. So the within person happiness variable to my random effects. And you could also do plus DC if you wanted to. So that's how you add like more random effects, but I'm not too concerned about that right now. Okay, so when I run this model, I get a summary, and again, I pasted it out here, and you'll now see that in addition to the intercept and the residual, you have the estimate for the random effect for happiness. I don't know why that took me so long to say. You'll also notice, and remember the tau stuff that we talked about, the variance of the random effects. You have the correlation between the intercept and, or the covariance between the intercept and the slope for happiness. And here again are the fixed effects. You can check to see if it changed much. Probably didn't change a whole lot, including the random effects, but it does open the door for thinking about between person differences in the effect of happiness on curiosity that we can go into in a moment. All right, so we're going to plot this result. For plotting, it can be useful to remove the missing data before you run the model. So that's what I'm doing here. I'm working with the same data, but now I am only looking at the data that has complete cases for the curiosity variable. And I'm not so worried about getting rid of rows with missing data now, because any lagging, I should have done any lagging that I needed to do earlier on, so it's not going to mess up any lagging. And so now I'm just running the same model. The results will be the same. And now I am into my data set, creating a predicted variable for curiosity based on model 3, so M3, and I do it using this function. So this is the name of my model, and I'm using predict. So now if we were to open up the daily diary data set, we would have a prediction of fitted values for our curiosity variable. If you don't take out your missing data before this and you try to merge stuff, it will give you warnings saying the length of your data sets aren't the same. Just makes it angry. Okay, so we're going to plot these data. So this is a data set. On the x-axis, we're going to have our happiness within variable, because we're mostly interested in the within person association. And then the y value is going to have the fitted values. We're going to do this for each person. And we're going to add a fit line. And we're just going to give names for x axis and y axis. And we're going to see what happens. Right, so this is, oh, I don't know if you're going to be able to see that. Here we go. Okay, so we'll just look at it over here, where now you have your happiness. And remember, this is a within person, so it's days happiness, where people's usual level of happiness is at 0. And if it's above 0, it's a day of higher than usual happiness. If it's below 0, it's a day of lower than usual happiness. And then we have their predicted curiosity scores. This is a value for the prototypical individual. So this is kind of the kind of estimate we get like from this part of the model. So it's for the average person in the sample, what is the association between happiness and curiosity? So on days of higher than usual happiness, your curiosity is higher than usual. These gray lines in the background, these are predicted associations for each individual. And you'll notice that because we allowed for random intercepts and random slopes, that people start at different places. And the angle of the slope is different between different people. Okay. Cool. So that's it. We ran, we looked at what multi-level modeling was. We ran a model and we got results, and we looked at a plot to help us interpret those results. We're going to do a bit more with the multi-level model in the next data lab. So we're going to end it there and have fun. All right. Yeah, I would run, for homework, I would run a multi-level model using 2 variables that you care about that are not curiosity and happiness, just so you can get some practice with it.